magnetic heating, and experimental investigation into an alternative method. Hello everyone, and welcome to a new project. Today, we will be investigating magnetic heating, whether it can serve as a viable alternative to conventional heating methods. The core material we are using is powerful neodymium magnets, known for their exceptionally strong magnetic fields. On average, these magnets can significantly influence particles around them. Our goal is to create a changing magnetic field around a copper pipe and use the induced effects to heat water, ultimately testing its capability to warm a small radiator. First, let me present the setup. I have prepared a section of pipe made entirely of copper. As you know, copper is a non-magnetic metal. Similar to aluminum, it is not attracted to magnets. However, you can create a magnetic field around it. The key principle we are applying is electromagnetic induction. If you constantly change the magnetic field near a conductor, you activate the electrons within it, generating an electric current. This is, in fact, the fundamental law behind generating electricity. Today's experiment will test if we can heat the copper pipe by rapidly changing the magnetic field around it and subsequently boil water flowing through it to lay the groundwork. Let's start with a simple demonstration of how electricity is generated with a magnetic field. When you cut magnetic field lines with a conductor at a 90-degree angle, an electric current is induced in that conductor. Here, I have a disc with magnets and a coil. As I spin the disc, the magnets pass by the coil, changing the magnetic field through it and generating a current, which lights this bulb. Notice that the light only illuminates when the field is changing when the magnets are moving. When they pass through a gap or stop, the light goes off. This change is crucial. Now, let's examine a related effect on an aluminum plate. Aluminum, like copper, is non-magnetic. At rest, the magnets have no visible effect on the sheet. However, when I move the magnets rapidly nearby, you can see the aluminum sheet itself begin to move. This demonstrates that motion or a changing field can induce forces even in non-magnetic metals. Furthermore, this interaction generates heat. As I continue to move the magnets near the plate, the temperature begins to rise significantly. You can see the thermal camera display climbing. It reached over 40 degrees Celsius very quickly and is hot enough to burn my hand. This heat comes from eddy current loops of electrical current induced within the metal by the changing magnetic field, which dissipate energy as heat. This brings us to our main experiment. We will use this principle of inductive heating on our copper pipe. By concentrating a strong, changing magnetic field around it, we aim to heat the water flowing inside. I have arranged powerful neodymium magnets around the pipe section. The important part is ensuring the pipe is positioned correctly within the magnetic field. I will now fill the pipe with water from one end. The concept is that as water passes through the section exposed to the alternating magnetic field, it will be heated, potentially to the point of boiling. Let's begin the test. I am starting the water flow and activating the system to create the changing magnetic field. We can monitor the temperature. Immediately, the temperature at the outlet starts to increase. You can see the water beginning to steam and bubble as it exits the pipe. Our water has indeed boiled. This confirms that the copper pipe, heated by the induced eddy currents from the changing magnetic field, can transfer sufficient thermal energy to boil the flowing water. Now, for the final stage of the project. Connecting this magnetic heater to a practical application, I am now linking the system to a small radiator. Two pipes will form a loop, one carrying hot water from the magnetic heater into the radiator, and another returning cooled water to be reheated. A small pump will circulate the water. Let's see what result we achieve. We start with the system at room temperature, around 19 degrees Celsius. As the pump circulates the water through the magnetic heater and into the radiator, the temperature begins to climb steadily. It rises past 40 degrees, then 60, and reaches up to 80 degrees Celsius. Now, it has hit 90 degrees Celsius. The radiator is emitting a significant amount of heat. In conclusion, we have technically demonstrated that magnetic heating is possible. We successfully boiled water and used it to heat a radiator to a high temperature. The copper pipe itself becomes extremely hot, so much so that its surface is shimmering and reflecting light due to the intense heat. In our setup, the outlet pipe reached 80 degrees, while the inlet pipe remained cooler, showing a clear transfer of heat. However, the critical question remains, One of efficiency. Is this magnetic heating method more efficient than classical systems like resistance heaters or gas boilers? That requires rigorous measurement and evaluation of energy input versus thermal output. This project was an exploration of the how, the underlying principles, and we have shown that by harnessing a changing magnetic field to induce eddy currents in a non-magnetic metal like copper, we can generate useful heat. It is a fascinating application of electromagnetic principles. I hope this has been a useful and thought-provoking project for your own experiments. If you enjoyed this investigation into alternative heating, please subscribe to the channel and turn on notifications for more content like this. Your support through likes, shares, and comments encourage the creation of more educational projects. Thank you for watching, and until next time, take care.